Hello everyone, my name is Samuel Dembowitz and today I'll be talking about Lab 5, Magnetic Braking with Faraday. In this video I'll observe and analyze a real-life system, create a computer model of the system through GlowScript, compare the computer model to the observed system, and describe the physics phenomena involved. The goal of this lab was to determine how a bar magnet can induce a magnetic force on a conducting tube, in this case aluminum foil. In order to do this, we needed to know the magnetic field of bar magnets, as you can see in this equation, the magnetic flux, in this equation here, the change in magnetic flux from a moving dipole, you can see in this equation here, and we utilized Faraday's law to find the induced EMF, and Lenz's law to find the direction of the induced current and EMF. We then calculated the magnetic force of the dipole and used Newton's third law to determine the force on the loop due to the dipole. The system of this lab was an aluminum foil and a bar magnet. The bar magnet weighed 0.0025 kilograms and had a magnetic dipole moment of 3.0986, which is from lab 3. The length of the foil was 0.3 meters and the width of the foil was 0.002 meters. The inner radius of the tube was 0.015 meters. I determined which end of the magnet was north and marked it with a Sharpie. I then held the aluminum foil tube vertically and dropped the magnet into the tube and recorded how long it takes to fall and repeated it 5 times. You can see the average fall time of 0.914 seconds, and you can see a demonstration here in this video. When creating the GlowScript model, I had to establish some constants of length, width, inner radius, magnet mass, and magnetic moment. I then also included the constants that we'll use in our formulas later. Next, I calculated the magnetic field through a function that takes the magnetic moment and the distance, calculates the B value, and then I calculated the change in magnetic flux by incorporating this equation here in the numerator and the denominator. I then calculated the gravitation force using mass times gravity in the negative y-hat direction, and then utilized this equation to determine the magnetic force on the loop due to the magnet. Lastly, I calculated the net force by doing net force equals the magnetic force plus the gravitation force, and then used this net force to update the magnet's velocity and position using Newton's second law. You can see the result of the program here. Interpreting the simulation, we see that the red current would be clockwise and the blue current would be counterclockwise. We know that the red current is the current from the bar magnet, creating a magnetic field downwards. Since the North Pole is facing downwards, it creates a magnetic field pointing downwards, and then we can use the right-hand rule to define the current as clockwise. The blue current is the induced current from the bar magnet, creating a magnetic field to oppose the change in magnetic flux through Lenz's law. This is the opposite direction as the red current, which means that it is counterclockwise. Flipping the magnet would not change the time spent in the tube, but the directions of the magnetic field and current would flip, since we have the South Pole now creating a magnetic field pointing upwards. The time in the tube from the computational model was 1.178 seconds, compared to the real-life experiment of 0.914 seconds. The computer model could be made more accurate by improving the accuracy of the measurements for the foil and the magnet, as well as some possible human error while analyzing the real-life videos. We can see on the right the velocity over time graph. You can see for about the 0.1 seconds, we had a negative slope, which means that gravity was stronger than the magnetic force from the foil, which means that the bar magnet was accelerating with a non-constant velocity. For the majority of the time, we see that there was a zero slope, which means that gravity was counteracted by the magnetic force from the foil, which means that the bar magnet was falling at a constant velocity. The first discussion question asked us if the resistivity of the conductor was reduced to as close to zero, how would it change the dynamics of the falling magnet? The induced current and magnetic force would increase, meaning that the magnet would fall slower since there was more force counteracting gravity. If there were holes or slits cut into the tube, the induced current and magnetic force would decrease since there was lower magnetic flux, meaning the magnet would fall faster since there was less force counteracting gravity. Thank you for watching.